chemistry of a battery creates a force that moves electrons out of the metal plate on the negative end and attracts them to the metal bump on the positive end. Electrons will start to move from minus to plus if the right kind of material is connected to the battery. Materials that allow electricity to travel through them are called conductors. Most metals are good conductors of electricity. Copper is the most common metal used in wires. In this animation, a conductor is connected to each terminal of a battery. Electrons start to move, traveling from the negative terminal towards the positive terminal. This is electricity. The electrons actually move from atom to atom as they travel through the conductor. This is a safety warning. Never connect a short metal wire between the terminals of a battery. This is a short circuit. The wire will get hot, you might burn yourself, and the battery will quickly lose its energy. Have you noticed the letter V on the side of a battery? This represents volts. Volts, or voltage, is a measure of the force moving the electrons. A AA battery is usually 1.5 volts. This is a low voltage, and that is why it is safe to handle a AA battery. Higher voltages are dangerous. Never experiment with anything that plugs into a wall outlet. Wall outlet voltages range from 120 volts to 240 volts. Extremely dangerous. Here is an example of a low voltage battery being used to create some light. Connecting a light bulb to this battery, we have created a circuit, a path for electrons to travel on.
Once again, chemical energy produces DC voltage. Let's take a closer look at how a cell operates. All cells contain two different terminals, or electrodes, immersed in a chemical solution called an electrolyte. The electrolyte is either a paste or a liquid. This cell contains electrodes that are immersed in a paste and is called a dry cell. The automobile battery uses a liquid electrolyte solution and is called a wet cell battery. This wet cell works on the same principle as an automobile battery. The electrolyte, in this case dilute sulfuric acid, draws electrons away from the copper electrode, causing it to become positively charged. The other electrode, made from zinc for this cell, gives up positive ions to the electrolyte, causing the zinc electrode to become negatively charged. The net result is that electrons are pulled from the positively charged plate to the negatively charged plate. If a load is connected between the two terminals, the electrons will flow from the negative electrode and will be attracted to the positive electrode. Once they reach the positive electrode, the electrons are chemically drawn from it back to the negative electrode by the electrolyte.
Hey, manganese dioxide, you look like you could use some electrons. I'd love some, but I don't know where to find any. Don't worry. Zinc has a bunch. I'll hook you up. Zinc. My friend manganese dioxide needs some electrons. I'll combine my negative hydroxide ion with you if you send your extras over. Yes, I really need negative hydroxide ions. The problem is that there isn't a path for my electrons to get to manganese dioxide. Look! It's the hand of God!
Oh my god! Oh my god! Oh my god! Oh my god! We're all gonna die! OMG! 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 Oh my god! Oh my god! Oh my god!
Now that there is a path, I'll send my electrons over to manganese dioxide. Bloop, 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 bloop. Okay, some of my atoms have a positive charge. Hand over your negative hydroxide ions, potassium hydroxide. Yes, you can have these negative hydroxide ions. Now I'm zinc oxide. And I'm potassium positive in water. Thanks, guys. Now I have a negative charge and the water I need to become dimanganese trioxide. Can I have the extra hydroxide ions that you didn't use in the reaction? Yes, I really don't need them. Bloop, 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 bloop. God is hungry. Bloop, bloop, bloop. Now we're done reacting. The battery is fully discharged. After all that, I'm still potassium hydroxide.
Track one. Track one.
There are two basic types of electrical current: direct current, or DC, and alternating current, or AC. In a direct current system, the electrons flow through a conductor in only one direction. Here's a simple example of how this works. As you can see, the electrons leave the battery and flow through a wire to a light bulb. After they flow through the bulb, the electrons flow back to the battery in a continuous loop. So you can see that in this example of direct current, the electrons are flowing in one direction only. DC electricity can be produced by a number of different devices. These include batteries, which are probably the most familiar source of DC energy, solar photovoltaic cells, and DC generators, such as those used in wind turbines and other small renewables projects. Using DC generators can be problematic since the electrical grid operates on alternating current. And so, when used in the grid, DC power must be converted to AC using a device called an inverter. The second type of electrical current is alternating current, or AC. In an alternating current system, the electrons periodically reverse direction of flow. The electrons flow through a material in one direction and then reverse their path and flow back in the other direction. This happens over and over again at a rapid rate. In fact, in U.S. systems, the current changes direction 120 times per second. Here's a simple example of how this works. As you can see, the electrons start out flowing through the circuit from positive to negative, but then periodically switch and flow back through the circuit from negative to positive. Again, this happens much more quickly than can be shown here. While DC electricity can be produced by multiple devices, AC electricity is produced only by AC generators or by converting DC electricity to AC using an inverter. With the exception of a limited number of high-voltage direct current or HVDC transmission lines, almost all of the electric grid today carries AC power.
Nikola Tesla was born on July 10, 1856 in the territory of modern-day Croatia to his two Serbian parents. Tesla grew up into a bright, inquisitive, yet eccentric child who found himself fascinated by the world around him. Tesla once tried to fly by jumping off the roof of a barn while holding onto an umbrella. He devised a bug-powered motor using June bugs, but had to abort his experiment after a friend decided to eat some of the bugs. Tesla once attempted to generate electricity by rubbing two cats together, which resulted in two very mad cats and a scratched-up Tesla. On June 6, 1884, Tesla arrived in the United States. He was hired by Thomas Edison to do basic electrical engineering, but moved up to redesigning the direct current generators that ran Edison's business. Edison offered Tesla $50,000, or about $1.1 million in today's currency, to make these improvements. After completing this assignment, Tesla asked about the payment for his work. Edison didn't pay out the money. He claimed that he wasn't serious about the payment, that Tesla didn't understand American humor. Tesla eventually left Edison's company and partnered with George Westinghouse in 1888 to commercialize his system of alternating current. The problem here is that alternating current competed with direct current, which Thomas Edison built his entire monopoly on. Thus began the War of the Currents. Edison started a massive smear campaign against Tesla and alternating current, trying to scare people away from using it. He spread false information about it, lobbied against its use, and went so far as to electrocute a circus elephant in public. Basically, Edison was a jerk. Direct current had plenty of its own faults. It was the cause of death of countless children and created numerous house fires. Also, the maximum reach of direct current was about 2 miles, which meant a substation had to be built to continue the current. To this day, they would still be building substations if they were going to get electricity across the U.S. Tesla's alternating current could go for hundreds of miles. Lights running on alternate current were bright white, unlike dull yellow lights running on direct current. Eventually, Edison had to give in to the demands of the people and had to go with alternating current. Tesla's influence spreads much further than electricity. He had over 700 patents and came up with ideas such as robots, spark plugs, the electric arc lamp, an X-ray device, bladeless turbines, wireless communication, laser technology, neon lights, remote control, cellular communication, radio, an electrical bath to remove germs, radar, and much more. Tesla died from heart failure in a room of the New York Hotel on January 7, 1943. Despite his fame and influence on the world, he died with significant debts and all alone. While Edison is known as the inventor of the century, Tesla is only acknowledged as a paragraph in today's history books, forgotten and unappreciated. Thus ends the story of Nikola Tesla, genius and inventor.